Sam?
Hey, yeah, here we go.
Yes, we can
Okay,
see your slides.
great.
Okay, please go ahead.
All right. Yeah. So thanks very much for the invitation to tell you about these a couple of recent papers that I have. So what I'm going to talk about is based on these two papers, one from last summer and one from just earlier this year, both with Sally Dawson, who I guess you'll hear from later today. And then the first one is also with Sam Lane, a grad student at Kansas, and the second is with Pier Paolo Giardino, a postdoc at Madrid. Okay. All right. So I probably don't need to motivate too much the the motivation behind considering the SMEFT to this audience, but just to kind of set the stage. I mean, as we've seen, the SMEFT is clearly becoming kind of some of the legacy measurements at the LHC, and the experimentalists are now presenting results in terms of constraints on Wilson coefficients, and this is all really exciting. So there's been lots of progress in just the last couple of years, but I think there's lots of kind of important questions that still remain on the theory side, both in kind of practicalities and how you do this, and also just kind of in better understanding, what we're actually learning from SMEFT fits. What does the space of models that UV complete the SMEFT look like? What's the best way to use these constraints for models of BSM physics moving forward? And ultimately, just overall, what are we really learning about BSM physics from constraints on the SMEFT? All right. So there's been lots of groups who have been working really hard to present global fits to SMEFT coefficients, including now the experimentalists. So here in our paper last summer, we had an updated global fit to all of this set of Wilson coefficients. So this is very similar in a lot of ways to some of the other fits that you've seen in the literature from other groups. A couple small changes and updates. So this now includes all of the Higgs data that was available as of last summer. It also includes some diboson data with full NLO QCD corrections taken into account in the SMEFT, as well as some other corrections to W and Z pole observables and the self-coupling. All right. And I want to pause for a second and take a short detour just to talk about the importance of these NLO effects. So the basic idea here is that frequently what's done is that the standard model processes that we're studying are known to NLO or even to higher orders. But often when we're doing these fits, this K factor to account for the NLO corrections, even in distributions, is just assumed to be kind of flat with respect to the standard model, from the standard model going to BSM points with non-zero Wilson coefficients. And the K factor isn't generally taken to be a function of the actual coefficients. And for some processes, this is totally okay. So here I'm showing a distribution of the PT of the W and W Higgs production. And you can see from going from the SM to some points with non-zero coefficients that the K factor changes by a little bit, but not very much. It's maybe a 10% effect. And the tails here. But in other processes, the NLO effects can be quite large. And this is really mostly a result of having the extra partons that can kind of really dramatically change the distribution. But in WZ production, for example, going to NLO and taking into account the effects of different coefficients. So these are just picking some kind of characteristic points that are allowed by the fit. You can see that the K factor changes by quite a bit. And this can actually have a real impact on the results you get by a fit to these anomalous couplings, right? So here I'm just showing the difference in a fit to WW and WZ data on these anomalous gauge couplings when I go from NLO and include the NLO effects. And you can see that it changes the constraints that you get almost by a factor of 2. So it's really important to use these full SMEFT and NLO predictions when you're setting limits. All right. So just going back for a second. So again, like I said, there's a number of global fits in the literature. And here's again an incomplete list of other references that have global fits, as well as ours. But again, I want to call back to the fact that, really we have all of these really nice constraints on the Wilson coefficients, but ultimately, the goal of this, is to really set limits on new physics. And so the rest of this talk is going to be talking about how do we interpret these limits in the context of particular models. All right. So this is going to be my strategy. I'm just going to kind of walk through how this process sort of works. And on the right-hand side here, I'm going to use this kind of very simple example of one such BSM model and talk about how it matches to the SMEFT, but you can set constraints on the physical parameters of this model. My easy example is just going to be, I'm going to introduce one vector-like quark that's a singlet and has the same charge assignments as the top, so you can think of it as just a right-handed top partner. All right. So I start with this model, and I'm going to integrate out this new particle at the matching scale. So assume that this top partner has a mass of a few TeV. I integrate it out, and this is going to generate at the matching scale a subset of SMEFT coefficients. And so this is the coefficients you get. You can see these three that have indicated with the green show up with a particular flavor structure, right? It's a top partner and it mixes with the top. So you generate coefficients with only the top quark in it, not flavor universal, and these make a big difference in the fit. And then for this one, I'm also going to include the one loop matching operator CHG. All right. So this is the list of coefficients that you get at the matching scale at a few TeV, but our measurements, of course, are done down at the electroweak scale. And so really what we have to do is, once I have this coefficients, I have to evolve these things down to the electroweak scale to understand what the bounds really look like. And unfortunately, we can do this because the full set of anomalous dimensions in the SMEFT has been computed by Trott and collaborators in a series of papers. I've just listed the first reference here. And so this evolution does two different things. So one, it changes slightly the values of the coefficients that are generated at the matching scale. So that can slightly change the interpretation of the fits. But it also induces new operators that are zero at the matching scale, but become non-zero when you're doing your measurements down at the weak scale, right? And this can be particularly important because some of these operators are really, really well constrained. And one example here is CHD, which is closely related to the T parameter. And so this is really, really well constrained by LEP and by diboson measurements. And so including these new operators that show up at leading log is really going to change what the constraints in this model look like. All right. So once I have the full set of operators that are evaluated at the weak scale, I can perform my fit to Higgs, diboson, and electroweak precision data and get these constraints on the set of operators that you have at the weak scale. But then I can reinterpret these as limits on the physical parameters of the model, right? So this full set of operators that I have at the weak scale is all functions of the physical parameters of this model. In this case, it's just the mass and the mixing angle. But I can reinterpret all of my bounds as bounds on those physical parameters, and that's kind of the goal. So I'm going to walk through this for a couple of different models, but first, just to kind of harken back to the same simple example with the vector-like top partner. So again, it generates these four coefficients at the matching scale. From the electroweak precision side, the electroweak precision data, what you get is in fact, it's really only sensitive to these two operators, CHQ1 and CHQ3. And actually at a priori, really the electroweak precision fit is only sensitive to this one combination, the sum of these two operators. And so you can see by the black dashed line that I have this nice constraint on the sum of the two operators. But in terms of the difference of the two operators, it's a completely flat direction, right? I really don't have any additional information. And that's just because I'm measuring, essentially I'm measuring one value at LEP, and it's just the Z to BB decay rate, right? But now what's going to happen is that once I have these different operators and I evolve down to MZ, you can see by these very faint gray lines that I'm going to generate non-zero values of CHD down at the weak scale. And these, of course, are really well measured by LEP. And so this kind of breaks this flat direction that you might think you have from the electroweak precision. And instead of this flat direction, you get this really nice constraint that I'm showing in purple. All right. The Lhc constraints are kind of qualitatively different. So here I'm not just sensitive to these two operators, I'm sensitive to all four. And so I've set a couple of these to correspond to this certain pattern that's dictated by this model, where they're all either equal to each other up to a factors of the top Yukawa. And now what the constraints look like, again, the kind of naive constraints that you get just from having these four Wilson coefficients are shown by this black dashed line. And then you can see, and that's just from the Higgs data. And then you can see that once I take care of the RGEs, it's going to shift the values of these Wilson coefficients down at the weak scale. And the black dashed line goes to this red dashed line. And that's just the effect of these Wilson coefficients evolving and slightly changing the fit that you get from the Higgs. But the other thing that's going to happen is, again, I'm going to generate these non-zero values of CHD and CH box. And then constraints from diboson data come into play. And that actually really qualitatively changes what the constraints in these Wilson coefficients look like. And the last thing I'll note here is that this nice tight blue curve is really mostly coming from diboson data. And that's exactly where these NLO effects are really important. So that they really do make a difference in the constraints that you get. All right. So now I have both the constraints from electric precision and from the Higgs and diboson data. I can put it all together and I get this nice tight constraint. I go from the purple and the blue curves to this combined constraint that I'm showing in green. Where again, I'm just using these kind of patterns that are dictated by the model just so that I can visualize this in a 2D plane. But really what's going on is that once I fix the mass of this heavy top partner to say a TV, there's really only one physical parameter left in this model, right? So I have, a priori this 4-dimensional Wilson coefficient space, and then after the evolution, there's a whole bunch of different operators that I'm setting constraints on. But ultimately, this particular BSM model is only sweeping out just a line in this, multi-dimensional space, and I can see it just basically going from the origin to some non-zero values as I take this mixing angle from 0 to slightly larger values, right? And ultimately, what's going to happen is I can see that I have this constraint on the Wilson coefficients, and where it intersects with this line of parameters that are generated by the model, that kind of tells me how large this mixing angle can be. So this is precisely how I set bounds on the Wilson coefficients. And here I can just do this as a function of the mass of the heavy guy also. And you can see that you get this nice constraint that the mixing angle can be about 10% at a TeV, and it varies slightly with the mass. Okay. So that's the simple story with this singlet top partner. Here I'm just kind of showing how the story changes just a little bit if I instead consider it a doublet top partner. So now I'm going to generate a slightly different set of Wilson coefficients at the matching scale. Really, the difference in all of these coefficients in the Warsaw basis is just that they're all have doublets as opposed to singlets. But you can see that the story is really similar here, right? I have this flat direction at LEP because I'm only measuring CHB but not CHT. I don't have information on tops from electric precision. But again, the RGE evolution generates these non-zero values of CHD, and again I get this nice kite constraint. And at the LHC, the same kind of story, right? The Higgs data, the interpretation changes a little bit once I take into account the RG evolution. But then the diboson constraints that come in from the new operators that are generated at the weak scale is really what makes a big difference. So the next big thing that happens though with this doublet is that now I have two parameters once I fix, say, the overall matching, the overall scale. So you can think of these two parameters as either a mixing angle both for the bottom and the top component of the thing. So there's two mixing angles instead of one, or I can think of it as just having one mixing angle and then a mass splitting between the two heavy quarks, the heavy top and the bottom, right? So like before, I have these nice tight constraints here, although actually here you see that all of the constraints are really coming just from electric precision data, setting the tightest bound. And again, I can kind of think about, moving along this line as changing the values of the mixing angle. But now I have a second parameter where I can change the mass splitting and go from a mass splitting of say 0 to 10 GeV. And this pink line shifts over to this yellow line. So instead of just line in parameter space, I can think of having a whole plane where if I, considered all of these different values of the mass splitting and the mixing angle, I would sweep out a plane in parameter space here. So now I can plot this again, as a function of these constraints on the two physical parameters, the mixing angle and the mass plane. And again, you see here in this case, all of the bounds are coming from electroweak precision, which is just telling me that this mass splitting can't be very, very large, and the mixing angle is correspondingly small. All right. My last simple example here, before I take a little bit of a detour with the singlet, is this case of the 2 Higgs doublet model. So here, all of the bounds are coming from the LHC, but the story is a little bit more interesting because I'm just going to fix a couple of these Wilson coefficients just for simplicity. But now in terms of CTH and CBH, which are sort of like modifications to the Higgsy collars, you can see that now I'm not just sweeping out, one parameter in this space. I can sweep out a whole bunch of different combinations of these things because there's a bunch of different types of 2 Higgs doublet models, right? I can think about changing from a type 1 to a type 2, and I can think about changing tan beta. So you can see here, I go from a type 2 with tan beta equals 1 to a type 2 with tan beta equals 5. And it goes from this blue to this pink line. It really changes by quite a bit the parameters that you're sweeping out in this plane. And moving back and forth along these lines is again kind of like the mixing angle in this case. Or for 2HDM, it's typically called the alignment parameter. All right. And here you can just see again that it's all of the constraints are coming from the LHC. The diboson effects don't make a terribly big difference, but you can see that the RG evolution changes slightly the bounds that you might get just from kind of a naive interpretation of the Wilson coefficients to accounting for these RGE effects. It changes the bounds slightly. All right. And again, I can put these in terms of constraints on the model parameters. So here, just in the alignment parameter versus tan beta plane. And these, if you're used to thinking about looking at bounds on 2HDMs from the LHC, then these plots are probably pretty familiar to you. They look really, really similar to the bounds that you get on actual fits to the 2HDMs. But I'll just emphasize again that these are really coming from constraints on SMEFT coefficients from this global fit that I did earlier. All right. So now I'm going to take a kind of interlude on the singlet model. And the singlet is really nice. And the reason I'm going to focus on it is just mostly because it's so simple, right? So we have this one additional state added to the standard model. And since it's so simple, it's really well understood. And it's kind of this nice test case for investigating details of the matching procedure. So the theoretical constraints on the singlet are really well known. And then more importantly, for what I'm going to show, the one loop matching results are also well known. They've been worked out, and the one loop matching has been worked out completely in a couple of different papers. And here, and the point of this story is basically this. So I have the Wilson coefficients that I'm seeing down at the weak scale. And these are coming from, again, I have the leading order, or sorry, the leading coefficients that I generate at the matching scale, plus these RGE coefficients that I have at leading log. And this is the stuff that I've been focusing on so much so far. But when I do the matching at one loop, I can also get these extra coefficients that I'm calling D here that have this extra factor of that have this loop suppression. But you can see that kind of there's no really reason to expect that these effects are any smaller than the RGE effects that I have here, unless this log is really big. So numerically, the question is whether or not these one loop matching effects can be important on interpreting these models. And I'm going to work this out. Since we have the one loop matching results for the singlet, we can see exactly what the numerical importance of these things is in the context of the singlet model. All right. I'm not going to spend too long on the details of the singlet. This is the full potential. I have, a whole bunch of different potential parameters. But after, once I find the physical states, really the ultimately what I have is something that looks like the standard model Higgs with all of its coupling suppressed by cos theta, and a new heavy scalar H has the same couplings as the Higgs up to multiplied by sine theta, this mixing angle. And there's a couple other parameters that kind of dictate the Higgs and singlet couplings to themselves and to each other from the potential, right? I mentioned the theoretical constraints. So these potential parameters aren't completely unbounded. And this is also kind of nice since this is well understood. I can see where in Wilson coefficient space these what parameter, what operators I'm actually allowed to generate from unitarity. And then I can also demand that I have to be at the electroweak symmetry breaking minimum. It is the global minimum of the potential, or else the singlet model doesn't make sense. We wouldn't kind of observe the universe that we do. And so you can see here, this white region is allowed, and at all of these other places, the electroweak symmetry breaking minimum isn't the minimum, and so this would be a problem with in conflict with all of our measurements, right? All right. This is just kind of showing how this allowed region changes a little bit as you vary the different parameters. The equations are kind of complicated, but there's kind of some qualitative features that are really somewhat easy to understand. Now for the matching. So in the singlet, there's two coefficients that are generated at tree level, CH box and CH in the Warsaw basis. And I'm focusing here. One detail is that I'm performing the match at the scale m, which is a potential parameter, and not at the physical mass. And for many values of these coefficients, these aren't too much different. Although if kappa is very large, then it can kind of make a qualitative difference here. And now once I have these two coefficients at the matching scale, they generate a whole bunch of operators at the weak scale. And I'll also just note here very quickly that when kappa is very large, the singlet is getting much of its mass from electroweak symmetry breaking, and actually it doesn't map right onto the SMEFT, at least at dimension 6, but onto the HEFT. And this has really been kind of nicely explained by a couple of papers, one of them just from last year. All right, so the tree level results. So I get these two operators, and then I take into account the RGE effects, and I get this nice banana-shaped region here that's showing the constraints. And the singlet model, as I change the mixing angle, is sweeping out along these lines here. And changing some of the potential parameters changes these lines a little bit, but not terribly much. And now I can see this kind of reinterpreted as bounds on this mixing angle. And this is just for the Z2 symmetric case. Okay, so the one loop matching again has been worked out by these two authors, one using the universal one loop effective action. And the second paper is actually just computes all of the one loop matching completely from Feynman diagrams. And this one loop matching does a couple things. One, it introduces new contributions to these operators at the matching scale, but also a bunch of other operators that don't appear at tree level. And in principle, these are of similar size to the RGE induced effects. And I just want to see numerically what difference it makes. So the only thing I'm going to pause on here is that we're only including the one loop RGEs. Two loops are really kind of necessary to do all of this consistently, but we don't know the anomalous dimensions at two loops. So we're stuck with this using the one loop RGEs for now. And you can see that the one loop matching can change the operators by 10 to 20% as they're measured at the weak scale. And finally, the effects on the fit. Here I'm just showing the two bounds. The colored regions are showing these theoretical constraints, and the bounds in pink are the electroweak precision fit, and then the black is the global fit. At tree level and dashed, and when I include one loop matching the solid lines, you can see that the effects are typically pretty mild, usually just like a 10% effect on the bounds, but they can be kind of bigger when I'm at these larger values of kappa. And here's just the effects in slightly different space in the mixing angle versus mass plane with different values of the potential parameters. And again, it's mostly a 10% effect that this one loop matching makes. Right. So that brings me to my conclusions. So of course, there's lots more things to do. I mean, there's a more robust understanding of what kind of coefficients can be generated by a bunch of different models, I think is really kind of in order and really interesting to think about. Including one loop matching for other models to understand if these effects can be different. Compare the effects to the size of dimension 8 operators. These are all kind of interesting directions for further study. So thanks, that's all I had.
Thank you, Sam, for the interesting talk. We have time for questions. Okay. So one from Eulalia. Can you unmute yourself?
Hi. Yes. I was wondering if you could go back maybe to slide 24 and say a couple more words about the matching scale for the one loop matching. Because there you show the plots with the, I think that's the dependence on, so the value that you get a low energy depending on the matching scale for just a few operators. But then in general, it means also that so depending on the matching scale that you pick, then you're going to have different patterns of the Wilson coefficients that you get at low energy, because each of them changes differently, right? So I was wondering if you looked at that a bit more, if you think there should be a way of including this as a theory uncertainty, for instance, how significant it is.
Oh, that's really interesting. Yeah. Yeah. So here, I mean, it's the matching scale, and I guess for us, it's also kind of like a pseudo physical parameter of the model, I guess, in the potential, right? But yeah, as you say, I mean, it is really interesting that you see this CH, for example, goes from, you know, a positive value to a negative value depending on how much you let it run, essentially. I should also point out, I mean, this effect, these patterns is kind of coming, this is the ratio of the one loop to the tree level matching -1. So it's, yeah, this is in some sense not the values of the Wilson coefficients that change a lot at the weak scale, but sort of just how much they change with respect to the tree level value. But you know, that's really interesting. I don't think we had thought about this as using it as kind of theory uncertainties, but that's one thing that you can imagine doing.
Yeah, so one of the reasons I'm asking, sorry, is because I'm working on something on another model similarly, and we are finding that there are some funny things. So if you change that really a lot in some regions, like if you lower it very much, you can open up new possible cancellations among the coefficients, which don't happen at other scales. So like it's something, maybe it's very pathological of the thing that we are looking at, and it's not general, but I think it's an interesting thing to explore.
Yeah, no, that's really interesting. Yeah, cool, thank you.
And Gauthier, you have a question.
Yes, thanks. I was so you did compare the effect numerically of the running and the one loop matching at the heavy scale. I was wondering if you also thought about comparing the effect of the running with the effect of the one loop, the finite one loop contribution at the low scale, at the electroweak scale. I mean, in particular, for instance, I was thinking of that when you made that statement that the electroweak precision observable only constrain the Z2BB bar coupling, which is a tree level statement, because you could also close the top loop there and get sensitivity. So is that something you plan or have looked at a bit already?
Yeah, I mean, so we don't have the one loop matching, I think, for the rest of these models, I guess. So like this one example with the top partner is sensitive only to you know, to this one thing at tree level, but at one loop, you, like you say, you get a bunch of extra things. So I don't know if I can say anything more about that. I mean, so for the Singlet model, we have the one loop match, is the only one where we have the one loop matching. As for comparing the size at the weak scale, I mean, here's this plot actually kind of shows, I guess, numerically what the difference is. So like at the matching scale, I go from, you know, so this coefficient, for example, in the Singlet model is 0 at the matching scale, right? Yeah. And then you can see, I mean, so it makes the shift at the matching scale, and then the evolution, I guess, though, is only at one loop, and so it's exactly the same.
Yeah, I mean, my question was more about the finite one loop contribution at the electroweak scale. So you can do this one loop matching at the heavy scale.
Oh, I see what you're saying.
And then at the low scale, you can again pick up finite correction.
I see. So I guess I should think about that as choosing a different scheme for doing your matching at higher loop. I
mean, I would conceive it as just a different piece of, I mean, it's independent, I would say.
Okay. Yeah, that's not something we thought terribly much about, I guess. Okay. I guess my feeling is that you could do this. You could consider the finite matching at the weak scale, but it, you know, it's to some extent, all of this is somewhat a little bit inconsistent when you don't have the two loop RGEs, I guess is the problem. So without those, I'm not sure exactly how you could do the comparison or understand that. But that is interesting to think more about for sure.
Thank you.
Yeah, thanks.
Okay, I think we should move on. So I see a raised hand from Mike, but I think we are like 4 minutes behind schedule. So I suggest that you guys discuss in the Slack channel.
Yep, for sure. Thank you.
Thank you again, Sam. And we move on to the next talk, Victor.
Hello.
You have worked out your. Okay, we can hear you.
Okay, perfect. Let me share my screen.
Please.